Okay, everybody. Based on what we mentioned before, you realize that in order to see how similar two signals are, you should go for the correlation explanation. Okay, as you see here, we have two different signals and the different values at different times. So in order to see how similar these two signals are going to be, we had the normalized correlation, and then we reached into the number of 0.95, and for these two signals we had the 0.38. And I told you that the limitation of the change of the correlation, the normalized correlation, is between -1 and 1. So when it's 1, it tells you that the two signals are exactly changing with the same behavior, and when it is -1, signals are exactly changing dissimilar in an opposite way compared to each other. And when the number reaches to 0, you will see that the two signals are uncorrelated. This is really important. So remember that at the time that this number is about 1, completely correlated, so exactly changing with respect to each other, and when it's 0, they are completely uncorrelated. So this is the basic idea that we are going to use in order to extract the information about the size of the nanoparticles which are dispersed within a medium. We told you that we have the apparatus here which shines the incident light into the medium containing the nanoparticles, and after that the light will be scattered and reach the detector, and the pattern will be formed. And I showed you the pattern as in this picture, and you saw that for the large particles, due to the slow motion, they have the slower movement within the medium, and the change of the scattered light will be slower. On the other hand, for the smaller particles, due to moving more rapidly and faster, you will see the change in the intensity, which is happening in a faster way. So this was the basic idea. Now I want to show you how we can get the information from these two patterns. Okay, although you see that these are happening randomly, but of course the pattern of these two are not similar. Okay, you see, it is obvious that we have the peaks and the maximums and the minimums here, which are far from each other. However, here you see how closer the peaks, the maximum and the minimums are with respect to each other. So we must find a way to extract the information. Well, before continuing to the mathematics of these two patterns, I want to make two assumptions here, and they are really important. Please keep them into your mind, because when we proceed, you will have to simplify the equations based on these two assumptions, and they will help you a lot, solve your questions. The first one is that as you see here, we have the light intensity which is fluctuating over a mean value. Of course, for these data set that we have here over this time, there must be a mean value around which the light intensity is fluctuating. So I want to introduce a line here and consider it as the mean value of the light intensity. I know it's not precise, let me move it here, but okay. Now I want to move this reference of 0 exactly on this mean value, and let me do this here now. I do this now. Okay, so you see that now the light intensity is fluctuating over the amount of 0. You know, this will help you for the next videos, that you will see some diagrams and some functions which decrease from the amount of 1 exponentially to the amount of 0. Maybe you will have the question into your mind that why they exponentially decrease from the amount of 1 to 0. Where this 0 come from? Well, of course, the light intensity never reaches 0, okay, but we can move our reference onto the mean value. Let me introduce the m here, and the mean value, we want to consider it as being 0. Okay, well, the second assumption that we want to make is that this mean value is not going to change with respect to the time. And this is really important, really important to help us to proceed. Well, please try to concentrate and keep your heads up. Please try to understand and think a little bit. The system here is now at equilibrium, which means that at any given time, the mean value of the light intensity is going to be the same, no matter that you have this set of data until here or this set of data until here. In both cases, the mean value is going to be the same. So I will write it down here for you. This is called the stationary statistics. This is an important assumption, and the reason is that the system is at equilibrium. So always keep it in your mind. And another assumption that we made is that the mean value is 0. So now let's proceed for the statistical and mathematical analysis of this pattern. Well, we want to use the concept and idea of the correlation only for this pattern. Within the previous video, I showed you that we had 2 different signals, and in order to see how similar these 2 signals are, we introduced the normalized correlation for 2 different signals. And this was the formula that we introduced. You see here, we had the square, the root square here in the denominator, and we had the 2 different signals, x and y. Okay, but within this situation, this condition is different. We only have one signal, and the important thing for us now is not how similar this function is with another function, because there is no another function, there is only this function. Okay, so what we can do is to use the idea of correlation and to compare this signal at time t exactly with this signal at time t plus tau. Okay, consider it as tau. I'm sorry, because I'm using the mouse of my laptop and I don't have the stylus, so this is the only way for me to write. So we want to consider this signal at time t and compare it with the value of signal at time t plus tau. And then we want to see how similar the signal is at time t with respect to time t plus tau. And if we compare these two signals at these two different times, we will see how long it will take for the signal to be dissimilar, to change, to become something else, to change its behavior. Okay, and based on that we can get the information about the size. Well, let me just tell you, if for the large particles you choose this time t, okay, let me use the lines. I am gonna erase this and use the time. Okay, and this time. Okay, well, just consider it as time t. Let me write it time t, and let me highlight it so that you see, and I will consider it as time t plus tau. Okay, so you see here that because we have the large particles, the signal at time t and the signal at time t plus tau for this pattern are somehow correlated. You can predict how this is going to change with respect to the time, because you see it's increasing, for example, here, and then it will be increasing, for example, here and here. Okay, so we can change the amount of tau within this period, within this range. Okay, and it gives us the information of the time that will take for the particle to fluctuate. So if we compare these two signals, how dissimilar these two signals are going to be with respect to the time lapse, with respect to the time delay of tau, then we will get the information about the size. Well, let's do it mathematically. But before that, let's have a look for these smaller particles. You see here that for the time delay of tau, there is no correlation between these values here. You see that here it is changing a lot, decreasing, increasing, decreasing. So you cannot predict the amount of the value of the light intensity by this time lapse. This is really important for us. Okay, so now we want to see how we can compare this signal at time t with itself at a delayed time of t plus tau, this delayed time. This is what we're going to do. And you see that we have the formula here, and we have the xt and the xt1, t plus 1. So this is the one function and again the function at a delayed time. However, here we had two functions, the x and the y, but here there's only one function and the delayed time. Well, the formula which is represented here is for the discrete form of the data. I mean that the data are not continuous. However, if the n goes to infinity, then these will be changed, transformed into an integral. Okay, now let's have a look at the slides of the course of nanomedicine offered by Professor Chelezi, and see how the integral forms are and how the correlation will differ with respect to the time delay. Well, this is the formula of the correlation function which is provided in the slides, and you see here that we have the function of the light intensity at one time, and again the exact function at the delayed time. Okay, so by multiplying them together and taking the mean by dividing them over t, we will get the correlation number of this function. However, the problem is that we have to normalize it, and I told you before that we introduced the normalized form, the power form, with the power of 2, which will help us to get more precise information about the size distribution. I don't know whether the quality of the film is now going to be good enough or not, but I just hope that it is going to be good, because when I tried before it was not. But you can follow these 2 or more 3 minutes from your slides, because now I don't want to change anything because the video is gonna be cut. So anyway, let's continue. Well, now we want to see how the correlation number is going to change by changing the delay time. So let's see what happens. Well, consider this picture, and this is the random pattern of the light intensity that we got, and this is the value at at the time t, and here the value at time t plus tau. Just imagine that I calculate the correlation with the delay time of 0. So I move this line on the left part to here so that they exactly overlap. Now that they exactly overlap, let's see what happens to the equation. Well, within this slide, you see here that it says at 0 delay time, equation reduces to this correlation. The intensity of light at time 0, again intensity of time at time 0, because this tau is going to be 0, and it is the intensity square at time 0. So this value is called the mean square intensity. This is really important. Let me show you in another form. Well, I told you about the assumption, the important assumption that we moved the reference on the mean value, so the mean value became 0. So neglect this one and neglect this one as well. So you will see that for the time that this delay is 0, we have only xt and xt which are multiplied together, and we will get the xt to the power of 2. Okay, and exactly here, if you neglect this one 0 and this one 0, okay, and again we will have the xt here and xt here, which will be multiplied with each other with the power of 2. So it will give us xt to the power of 4, and because of this square root that we have here, it will give us the xt to the power of 2. So here in the denominator we had the xt to the power of 2, and here again we have the xt to the power of 2, and it will give us the xt to the power of and it will give us finally the R1 with the final value of 1. Okay, remember, because this is really important. So I want you to remember that for the delay time of 0, that these 2 points are completely overlapped, so it's the delay time is 0, and we come here, we will have the correlation value of the mean square, which is exactly stated here in this slide of Professor. You see here that we have the mean square. It is stated here, it is the mean square intensity, and because it is normalized, okay, we have the is to the power of 2, and here it is normalized to the is to the power of 2. We will get finally the correlation, the normalized correlation as 1. So for the delay time of 0, I want you to remember that the final value is going to be 1. Okay, now let's see what will happen if we increase the delay time. Please be conscious and concentrate, because this is going to be really important and a little bit complex. Well, when we increase the delay time, you will see that the correlation between the signal and its delayed time signal will be lost. You will see that the signal will lose its memory. What do I mean? as we showed here, within this signal, at the time t here, when we increase the time delay and for example come here, we cannot predict the values of these light intensity based on the value that we have here. It will be impossible because the system loses its memory, because the characteristic time in which we are analyzing the light intensity, it is longer than the time that the particle needs to fluctuate. Just imagine if you have one particle here, okay, at this point, it takes time for the particle to fluctuate and change the light intensity to become here. If you are measuring the light intensity in a period of time that is longer compared to the fluctuation of the particles, then you will not get the correct correlation. You will lose the memory of the signal. This is really, really important. So, what will happen to the correlation? Well, we told you that we have the assumption that the mean value here is going to be 0. We considered that. Now, with this assumption in mind, let's see what happens. Well, for the time that the delay is much greater than the typical fluctuation time of the particle, and as a result the fluctuation of the intensity, fluctuations are uncorrelated. So it means that you cannot predict the value with the present data that you have. It means that you lose your memory. So when you want to calculate the average of two functions which are uncorrelated, okay, we have the multiplication here, you can calculate the average of each one and then multiply them together. We made the two assumptions. The first assumption was that the value of the mean, the average of the light intensity, is not going to change with respect to the time because we have the stationary statistics, because the system is at equilibrium. The other assumption that we had was that we moved the reference on here, the 0 value for the average. So now you see that due to the system equilibrium station, due to the stationary statistics, the average value at time 0 and at time tau, the delayed time, they are both the same. And we will reach now to the square of the mean for the delay time much greater than the typical fluctuation time. So again, I'm telling you that for the delayed time 0, we reach to the mean square, and for the delayed time greater than the fluctuation of the light intensity, we reach to the square of the mean. And because we made an assumption that the light intensity has the average value of 0 at all the time, this number is going to be 0. So we can say that we decay from this number, which is not 0, to this number, which is 0. And this is the results that we get. Now you understand why the correlation decays from the value of 1 to the value of 0 as the time delay. This is really important. Let me add it here for you. As the time delay increases from 0 to infinity, but this infinity is compared to the fluctuation time of the light intensity. So you see here that for large particles, the decay is getting longer compared to the small particles, and this is because the large particles maintain their memory longer compared to the small particles. The large particles, due to having smaller diffusion coefficient, are moving slower within the medium, and as a matter of fact, the light intensity is fluctuating more slowly with respect to the time, so that at larger time delays there is still a correlation of around 0.5 between the signal and its delayed time of tau here. So it will get longer time for the signal to lose its correlation. It will take longer time to lose its memory, so that we cannot predict the future amounts. However, for the smaller particles, due to having larger diffusion coefficient, their movement within the medium is faster, and as a matter of fact, the fluctuation of the scattered light is more rapid, and you see that it will take really shorter time for the particles to lose its memory, to lose its correlation. You see that at this time that the smaller particles almost lose 90% of its correlation, the larger particles still have a reasonably good correlation. So it means that they maintain their memory. Now, if we plot this correlation decay within a semi-log plot, we will get some interesting information that I will continue within the next video. I'm really sorry for this video to take for about 34 35 minutes, and please try to think a lot about what was said, try to understand, and try to understand why you have to compare the signal pattern with its delayed time. You want to see how similar they are with respect to the time, because when they are not similar, this is the time that the signal is going to change, the fluctuation is going to change, and this gives you the information about the size, because based on the size and the movement of the particles, the light intensity is going to change. And based on how fast the time intensity changes, you will get the information about the size. So they are related to each other. Now let's finish this video and we will continue within the next one.